Hi everyone, we are back, and so we've basically watched the video from our lab handout on DSC. We looked at how the experiment was performed, and now let's get into kind of our data analysis. So let's go ahead and look at the data that we have available, and let's figure out how we're going to basically look and perform this experiment. So let's go ahead and get this guy downloaded. Let's open it up here. All right, let's look at, actually let's go back a step. And then now let's extract all this data. I'm going to put it on my desktop, and I'm going to make it, I'm going to do a new folder, DSC data, and I'm going to put it in here, and then let's go ahead and extract everything there. So now I can go to my desktop and let's take a peek at the data that we have at our disposal. So we have basically these 2 or 3 different types of data. So first is an image. So let's look at what the image looks like. So we can look in here, looking at this image, one of the key parameters, actually I'm going to change my pen here. The key parameter that we want to look at is this enthalpy of formation, or the heat. So this is basically the integral of this curve. So this is equivalent to our delta Hm of formation. Now, look at the units. We're in this kind of weird microvolt seconds per milligram. So this is the value that we need to multiply by 0.3 in order to convert from these weird units to our joules per gram or kilojoules per kilogram for enthalpy of fusion. So that's what we're going to utilize these kind of image plots for, just this. So you're going to utilize that, and then we're going to figure out, okay, what material is going to be appropriate for your particular application. So I'm going to leave without saving because it's no big deal. So let's go back to our DSC data here. The other data that we can see are these, the other thing that we can kind of see here is our, basically we're looking at our raw DSC data. So you see we have time, sample temperature, heat flow, and then our kind of baseline measurements. So what we want to plot is essentially our heat flow versus temperature. Like that's what we want to plot. And again, you can see that these units are in microvolts. So again, we need to multiply this by that 0.3 factor in order to get to our milliwatts values. So these are kind of the raw data of just a single run. Now, you'll also see one more type of plot here. And you see the cycle. So this cycle data is a little bit larger in scope and actually values. So you can see here that we just have our temperature and heat flow, no baseline here. So what we did here was we heated them. We melted, we cooled, and we melted and cooled again. So we're going to look at that to assess 2 kind of things. We're going to look at thermal stability. Excuse me here. We're going to look at thermal stability, and we're going to look at the degree of supercooling with these cycle data. So let's go ahead and let's look and play around and let's see what we can work with. So I'm going to kind of sort this data, and I want to also sort it by name as well. Actually, let's just sort it by this. So what I want to do is, looks like I'm going to first copy in. So I'm going to also open up my handy. Let me just delete this other notebook. This is our Mathematica notebook, and unlike many of them that I post here, it's actually pretty well commented. So we want to paste in our raw Excel files of only the non-cycle data. So I'm going to go ahead and we're going to do increasing amount of stearic, as you can see here. So I'm going to copy in here. I'm going to paste in my notebook. So let's go. I've got too many files open, as you can see. Very, very busy week, but very, very exciting week. So this is 90 stearic and then 10 caloric. And you can see this is 10 stearic. Actually, it gives a little bit of an issue. So you want to reformat that in a very kind of unique way right here. And then let's kind of paste that in there. And then range from 0% caloric to 100% caloric. So actually 0% stearic to 100% stearic. So if I'm at 0% stearic, I need to pull up my file. Unfortunately, quite a few of them. So I want 0% stearic. So that is going to be 100% caloric. So again, the files, the way that they're named, let's go back over here. So, oops, let's go to the files that are named. It's 10 weight percent stearic, 90 weight percent caloric, 20 stearic, etc., etc., etc. And then And you'll notice I'm not touching the cycle files yet. So that's kind of the key idea here. So I'm going to go ahead and put it like this. So it's from 0% steric to 100% steric. So Shift Enter, this is my raw data list. So if I can import, so my dlist 1. So for example, I want to look at my data. So look at the data. Let's look at 1 to 50, and let's look at table form. Oops, let's go ahead. Why isn't it like that? Actually, let me go ahead and flatten 1. Actually, let's go ahead and do that here. So I am going to go ahead and basically just read in this function. So this is going to be my raw data. So reading in my raw data is taking a little bit. So this is my raw data. So RDAT, let's look at RDAT1. And actually, let's look at 1, 1. This is basically getting rid of parentheses. So now I could do, let's say I could take 1 to 50. So let's look at it in table form. So as you can see here, I've got some junk and header at the top because I want to plot it in terms of sample temperature versus heat flow. So I want the 1, 2, 3, the third and the fourth column. So let's go ahead and say, let's go to 13. Okay, here we go. So I've killed off almost all my headers. So now I just want a 14 column. So let's say 14 to 50. So this is great. So this is the first column, second column, third column. So I want basically I'm going to do this, all 3. And that's just going to give me all my temperatures. And instead of 14, I'm just going to go to -1. So these are all of the temperatures. So I could kind of go ahead and look at that. And let's plot this. Let's just take a look at this. So list plot. And again, you could read through kind of how, I've kind of basically I've commented this quite a bit. So you could read through these, but I just kind of want to look at what does my temperature look like. Well, it looks like exactly what we did in the experiment, right? So we ramped up from room temperature to 100, and then it cooled back down. So that's my temperature. So the third column. So what this is doing is reading in for each of my data sets, bring in the 14th column, give me all of my rows, and then the third and the fourth column. So if I do the fourth column, this just looks like and I'm going to multiply this by times -1, because again, endotherm down, exotherm down, we can do kind of plot range all. So I have my plot here. So this is essentially my kind of the first data set, this pure 100% lauric. And we can kind of see where it melts as a function of temperature. But you can see, again, we want endothermic up because melting is an endothermic reaction. So endotherm on the top, exotherm would be negative here. So if we were freezing and solidifying, essentially. So this is kind of what we're wanting to plot. So we want to plot this time versus temperature. So, or, basically we want to plot our heat flow in units of milliwatts to versus temperature. So temperature is fine, but again, we have these kind of weird units of microvolts. So this is where, again, we're going to have, from the indium baseline, we're going to convert to milliwatts. So we need to multiply by 0.34 or 0.3, excuse me. So that's why we're saying here, we're going to multiply, what we're going to do here is take this, we're going to keep temperature the same, but we're going to multiply the x or the y-axis by this -3. So now that'll give me a nice looking plot, like so. I'm going to zoom out just a little bit, and let's go right here. So this is now where we have to kind of see the peaks. So let's look, again, as we're kind of going through this data set, let's look at the first file. So this is 100% lauric. So we could go back through our DSC data, 100% lauric, and we can make sure and confirm. Remember, this had exo up, endo down. We're flipping it here. So we can figure out the heat of fusion by multiplying 21.814 times 0.3, and then we'll get that value. We can deal with basically to calculate the enthalpy of fusion, so the area under that curve. So now let's go back to what we kind of also want to do with this phase diagram, or actually with these Mathematica notebooks. So my notebook is thinking, now it's not responding. That's why we always save. Okay, so let's get back to this plot again, so we can multiply that value, and we've kind of seen that before. So the other thing that I want to do is to start to build up a phase diagram. So we are going to be plotting as a function of concentration of stearic. So this is 0 stearic because I'm looking at the first data point, which is 100 lauric. So I want to look at the melting temperature of lauric acid, and we should expect that to be lower, and we kind of see that it's a little bit lower as well. So this first point, because it's a pure material, this is kind of just a kink in the data. It kind of always shows up for lauric, but I see a single peak here. I'm going to ignore this kind of peak because it's a single phase material. So I know it should melt congruently, so there should be a single peak. So I'm going to go ahead and click here, and I'm going to copy. So I, basically I did right click, get coordinates, or so right click, get coordinates. So I'm going to click here at this peak, and I am going to grab out, I want to see the temperature, i.e. the x-axis value where that occurs. So for example, I'm going to paste in here, and this is my y-axis value, but I'm melting here, it appears at about 47.2. So I'm going to go ahead and paste that into here, and what is going to be that point? Well, that is going to be my liquidus line, right? Because I'm going to melt, I'm going to go from solid to liquid. So that's going to be my liquidus point. There's not going to be any solidus point because I don't see 2 peaks. I don't see any other intermediate peaks as well. So that is going to be my first temperature value at 0% stearic acid. So now let's go to the second file. So 10% stearic acid. So I'm going to go ahead and click here, go ahead, RDAT2, and lo and behold, I kind of see like almost 2 little peaks here. So I see a little hump here, so I'm going to call this one peak, and I see a peak right here as well. So I'm going to go ahead and Control C. I'm going to go down. I'm going to copy these values again. And then, so now, which is so again, on this side, what am I? Solid. So I cross first the solidus and then the liquidus. So the highest temperature peak is going to be my liquidus. So I'm going to go ahead and paste that in here, put a comma. And my lowest temperature peak is going to be my solidus. If I have 2 peaks, again, I'm going to have a solidus and a liquidus. So those are kind of my values. Let's go ahead and look at the third. So, because that's going to be my 20% stearic. So let's go ahead and click here. Ooh, looks pretty, again, there might be 1 or 2 peaks here, but this looks like pretty much like a single peak here. So I'm going to go ahead and click here. So this is interesting. It appears like I only have 1 peak. So what type of transition is that? So if I go directly from a liquid to a solid, well, that's going to be my eutectic point, perhaps. So let's go ahead and see, paste that one in here. So I can go ahead and click that in here. So that's going to be my liquidus. And then there's going to be, again, an Na. I want to make sure that each of these is, so I have right now I have 1, 2, 3, Na, Na, and then Na. Not applicable. What about 3? Or actually 4, our 25 composition. Actually, let's make sure that we are looking at 25. Yep, exactly here. Now, here you kind of maybe see perhaps, so I have a peak here. You might classify this as a peak here, but you might have like these 2 kind of eutectic points. So let's go ahead and let's paste that in here. So again, very, very similar. Actually, sorry, let me paste it. Get coordinates, click. So I'm going to go ahead and click here. So you might have 2 eutectic points, or we can kind of go back. So 42.3. So this is a little bit lower. We might be able to see that might be my eutectic. Let's go back to kind of this diagram here on number 3. But again, it's kind of your choice. So you could see like there's a little bit of asymmetry here, but we'd have to really kind of zoom in on this graph to kind of see what's going on here. So there might be a little peak here. There might be a little higher peak, right here. There's like a little bit of a hump going on. So you could pick, for example, like right here, maybe something like right here. So those could be the temperatures as well. So let's go ahead. You could plug those in previously and kind of compare those values. Oops, let me paste it. So again, we're looking at the y-axis values. So it could have been a solidus and a liquidus here. But again, it's not too big of a deal. So we could just kind of say that there's Na, so 1, 2, 3, 4, 1, 2, 3, Na, for example, and then 4, Na, and then Na. So we had 1, 2, 3, 4. Let's look at our fifth data set. So again, it's kind of up to your interpretation. Sometimes it's hard to kind of differentiate. One of the ways that we could actually improve our data set is by actually looking at and starting to kind of create by basically going at a slower heating and cooling rate. So I'm going to control C here, I'm going to control C here, and again, this is my lower temperature, so this is going to be my solidus, again, finally, and then my liquidus, highest temperature peak, go from solid to liquid, it's going to be right here. So you could start to kind of plot this. I'm going to do Na. Actually, I'm going to stop. Do Na. Get rid of this, get rid of this. So you could start to kind of transpose this list. So I could transpose composition, and right now I just have 1, 2, 3, 4, 5 values. So 1, 2, 3, 4, 5 values here. So I could kind of, I'm going to go ahead and create another comp right here, where I'm just going to get rid of the first 1, 2, 3, 4, 5. So I'm going to go here. I'm going to do the transpose, and then I'm going to shift enter this. And you can see I'm starting to kind of create this phase diagram, right? So you can kind of see liquid, liquidus, and then it's going to pop up. And now let's do one more. Let's look at 6. So now we clearly have, again, still got these kind of two peaks going on here. I'm going to click here and click here. I'm going to control C. I'm going to look over here again. I've got my solidus here. I've got my liquidus here, and I've got this here. I'm plusing 273. I need my Na. I need my Na, and then I'm going to get my 40 here. So shift enter, and things are kind of looking right. Liquidus line, solidus line. So you can kind of build that up. Again, there's some kind of discrepancy here. There's probably a little lower peak. Actually, if I want to go back and look at that, our 2 data set here, actually this one right here, I'm going to go ahead and replace, we had that 42.7. I'm going to say that this was our liquidus, and then we actually had a, here would be my solidus value. So let's see how that looks and see if we, yeah, it looks a little bit, kind of clunky. Maybe it's a little bit kind of lower, but again, actually I'm going to go ahead and undo that. Undo, and keep that value there. Let's see how we're looking. Yeah, that's looking a little bit better. So anyways, let's do one more. So now I can see I've got actually a couple of peaks. So I can go here, 1, 2, looks like a peak maybe right here, and then here as well. So I got 4 peaks here. So now again, if I have 4 peaks, I want to organize them, highest temperature peak is 56, that's going to be my liquidus. So I'm going to kind of control V here. My solidus is going to be right here. And then my intermediate 1 is going to be the next highest temperature from the solidus. So it's going to be this. And then my next highest intermediate temperature is going to be this. So I can put the 50-50. So again, now I'm starting to kind of build this phase diagram. So you can see kind of how the liquidus looks like, how the solidus looks like, and how we're going to kind of build up this phase diagram. And you want to kind of connect that and compare this with the data that you'll basically obtain from the Costa paper. So we can look on our Canvas site. I've got that here. So if we look at our DSC lab, we have the Costa paper. So you can compare essentially the phase diagram that you're going to generate to the phase diagram that's in this paper. So once this loads up from Canvas, so let's go ahead. So this is going to look very similar except flipped to our phase diagram. So you can kind of see these kind of intermediate temperature points. Here it's actually the phases are deduced using this kind of Raman spectroscopy technique, or you could use XRD. So those intermediate temperatures could be, liquid and solid, as we know. Those can be, again, this, solid-solid solution, FCC, BCC, HCP, steric, peritectoids, eutectoid transition, or actually eutectoids and peritectoid transition, solid-solid transition. So you're going to build up that phase diagram, and then you're going to kind of connect the dots and then kind of compare that to the data that's kind of seen in the literature value. So this is fantastic. And then again, you want to build a phase diagram. We want to kind of pick an application and then see what are the thermal properties, right? We want to look at what is the enthalpy of fusion? What is our melting temperature? The melting temperature is the most important for these applications. So once we pick a melting temperature, that determines, our phase change material, our PCM material. So it is going to regulate the temperature at whatever the melting temperature is. So if I have an application, for example, where I need it to melt at 42.3 degrees, I want to pick something like right here, where there's a single kind of melting point here. If I need a higher temperature application, I might look at, for example, the last data set, which is pure steric, which has a very, very high melting temperature around, like, again, we can look over here at around 73 degrees C. So if you have something that requires a warmer temperature to be regulated at, we want to use that type of material. So, but in addition to the enthalpy of fusion, which we're going to calculate, the enthalpy of melting, which we're going to calculate by taking that integral, multiplying by 0.3, and additionally, in developing this phase diagram and figuring out the melting temperatures, we also want to look at two kind of quantities, which is thermal stability and the degree of supercooling. So I'm going to go ahead and now I'm going to pull in my cycle data. So now I'm just going to grab all of my cycle data, and I'm going to paste it into this notebook here. I'm going to kind of use the same type of basically code that we've just previously developed. But let's look at first the 100% Loric. So it's kind of hard to see here, but what's going on is we're going to melt, then we're going to cool, and then we're going to melt again. So thermal stability is essentially a measure of how stable is kind of these melting and basically these melting and cooling and freezing properties. So as a function of multiple cycles. So you can see here the graph reproduces itself quite well. So this means that this PCM material is going to be thermally stable. I want to use this in an application where, for example, I need to embed this material into walls and keep it at room temperature. So I want this material to be able to kind of melt, solidify at the same temperature over and over and over for tens of thousands or even millions of cycles. Because if there's shifts in between each cycle, then who knows? In 5 years, my room might be at 100 degrees C or minus 100 degrees C. So we don't want that. The other property we see here, which is very weird, which is, I melt at 46.5 degrees, but then I solidify at 43 degrees. This is weird, right? Like ice, I know ice should melt and solidify at 0 degrees C. So why, there's only one melting temperature and one solidification temperature is the same. So why is there this difference? Well, this is the degree of supercooling. So the degree of supercooling is the difference between this peak right here, 46, minus this peak right here, 43. So why is there this difference, this 3-degree difference, this 3-degree of supercooling? Well, it's all about the kinetics, right? We're running this experiment at 10 degrees K per minute. So we're melting quickly, and then we're cooling down quickly. And before we're giving time for the atoms to kind of rearrange and solidify, we're already past kind of our melting temperature. So there's this kind of kinetic factor in addition to the thermodynamics. So if I were to slow this down from 10K to 0.01 K per minute, my degree of supercooling would be much less. So my line might end up like right on top of each other. But if I increased my basically heating and cooling rate to 100 degrees K per minute, then I would be you'd have a large degree of supercooling. So as I increase essentially the heating or cooling rate, I am going to increase my degree of supercooling. As I decrease it, I'm going to decrease my degree of supercooling. So you want to consider this in your application as well. So what is the time, right? Are we heating and cooling really, really fast in your application? If so, we need to make sure that our degree of supercooling is relatively small. So 100 is pretty good. Actually, 100 Loric is really good. So is 100% steric, but we kind of run into some issues when we look at our last sample. So thermal stability here, you can see it's horrible, right? So I heat up, I cool, and then I heat up again, and there's some shifting in these parameters. So I wouldn't use this for an application where I need to basically heat and cool or change phases for many cycles. So I wouldn't use this for my wall application. And you can see for the eutectic, it's actually pretty good for the eutectic. There's a little bit of a shift, but again, it's better. And why is that? Why is the eutectic and these pure materials better than 50/50? Because again, we're going from like pure liquid to solid. We don't have this kind of solid phase transitions and other things going on here. So you want to create a phase diagram. You want to kind of quantify some of these properties, and you want to create a beautiful kind of poster similar to kind of what's seen on our Canvas site. So we want to kind of analyze some of these PCM properties. We want to pick an application. We want to describe how we did the experiment. We want to explain how did you determine the enthalpy of fusion, create this phase diagram. You also want to kind of discuss how did we essentially calculate degree of supercooling and thermal stability, and then create a table where we kind of pick a particular composition that hits our parameters that we want for our specific application. So with that, that is the end of our PCM. So create a beautiful poster, and I will see everyone basically on our poster session day, and I'll grill you with questions. Super hard questions. No, I'm just kidding. It's going to be really fun. So I will see everyone then, and I can't wait to see some great posters. Thanks. Bye.